What's up, everybody? Welcome back to yet another episode of Basic CHEM 101 with Sihlebonani. My name is Sihlebonani, and today we'll be dealing with the wave nature of light. Let's get to it.
Let's go. This is how every child that wants to make it one day. Zimbo say class and presence of mind is elsewhere. Bring out Uzuzani, Abna Ode, Already Alispani, and the timer is nowhere. I know your pain, you don't have to be scared. The dreams are very pure, they the written and focus. Keep that pen and paper, they will take you to that day. In the meantime, stand up, heaven.
Imagine it's New Year's Eve, going into the new year. It hits 12 midnight. You look up. What do you see? Beautiful colors of firecrackers, right? Well, as for a chemist, they see the burning of metal compounds. They see a deep red color. They think of lithium and strontium compounds. They see green. They think of barium compounds. So even at our social gatherings, a chemist can still try to determine the compounds that are involved in certain aspects of such an event. So this leads us to studying compounds in the presence of light. But for us to do that, we have to understand the nature of light itself. This can help us understand the formation of chemical bonds and the electronic structure of atoms. This can also help us in understanding what is the use of electrons around the nucleus. So this is the topic for today, the wave nature of light. So light on its own has a dual nature. So we'll deal with the first one today, which is the wave nature. So what is a wave? A wave, we've seen a wave maybe in the ocean or when you drop something in still water. There are oscillations that occur or a continuous repeating change in a physical field. So light as well, it occurs as a wave. It consists of oscillations in electric and magnetic fields. So light is a wave. So if this is your wave, the distance from here, which is your peak, to an adjacent peak, this would be your wavelength. So a wave has a wavelength, which is the distance between two adjacent peaks or two adjacent troughs. So that is your wavelength. So your wave has a wavelength. But the number of waves, if we say from here to here is 1 second. So the number of waves that pass through a fixed point would be called your frequency. So the number of waves that pass here in 1 seconds would be called your frequency. Now if this is 1 second and you have so much waves, you can say the frequency here is very high. But if in the same 1 second you have waves like this, you can say here the frequency is low. Now if you look at wavelength and frequency, you can say that your wavelength, they usually denote your wavelength as the sign lambda, and then your frequency, they say it's the sign nu. Now if this is 1 second and this is 1 second, what you can deduce from here is a wavelength is actually inversely proportional to your frequency. Now, mathematically speaking, when you say this, there is an inverse proportionality. So it means a wave is equal to, when you replace the inverse proportionality sign or the proportionality sign, you have to put a constant. So in this case, the constant would be the speed of light. Now a constant has to be, now a constant has to be independent of the variables, in this case, which is your wavelength and frequency. Now the speed of light here would be 3 times 10 to the power 8 meters per second. Now, how does this help us? If we say light consists of oscillations in the electric and magnetic fields, so light forms what is called your electromagnetic radiation. So a specific color that you see in those, let's say, those firecrackers, when you look up, actually has a specific wavelength and frequency. So if you understand the relationship between the wavelength and frequency, maybe you can be able to look at a color. If you know its wavelength, you can be able to calculate its frequency. Now let's try and do an example of the relationship between wavelength and frequency. So your example would be, let's say, yellow sodium emission gives us a frequency of 5.09 times 10 to the power 14 per second. So this is your frequency. Usually your frequency is written as per second or in hertz. Then another example would be to calculate. So if the frequency is this, they would say calculate the wavelength of such an emission. And then if they give you the wavelength of the violet light, which is 408 nanometers, they would say calculate the frequency. So with what you know, so for your number one, which is this one, you know that your wavelength is your constant divided by frequency. Your constant is 3 times 10 to the power 8 meters per second. Then your frequency is 5.09 times 10 to the power 14 per second. So you get your answer, because its length, it will be in meters. So you will get your answer as 5.89 times 10 to the power negative 7 meters. But you can rearrange this to be 589 nanometers. Nanometers is times 10 to the negative 9. Then for this one, which is your number 2, your violet color, it means we are looking for your frequency, which would be your C over lambda. Then 3.00 to the power 8 meters per second divided by 408 times 10 to the negative 9 meters. You get 7.35 times 10 to the power 14 per second, or 7.35 times 10 to the power 14 hertz. So that is how you would calculate your frequency or your wavelength depending on what you are given. Once you do a lot of calculations, you will understand that once you have very short wavelengths, then they go to be longer as you go. Once you get your very short wavelengths, you get high frequency. Then once you get your high frequency, you'll also understand that your high frequency wavelengths, as you go to your low frequency wavelength, you have what is called your electromagnetic spectrum, where you have in the high end, you have your gamma rays, and in your lower end, you have your TV or radio waves. And somewhere in between, you have your visible light, which is what you can see with your naked eye. So your visible light will be from your violet to your red color. So this would be your, so somewhere here you'll have your ultraviolet, which is your UV. Then here you'll have your infrared, which is your IR. Then you have somewhere your microwaves. And then somewhere here you have your X-rays. So you find this visible light would be somewhere in between your 400 nanometers to 800 nanometers. That is your visible region in your electromagnetic spectrum. And then the wavelength, it gets smaller this side and it gets longer that side. So the frequency, it gets higher this side, it gets lower this side. So that is your wave nature of light. And I think from now we will stop at that point, understanding the wavelength and the frequency and the wave nature of light. Thank you very much for watching. Please, if you have not already, please subscribe. And if you got something out of this video, please like and please share. Even if you have not subscribed or not liked this video, please share so that it gets to someone who might need some clarity on a few things. This has been Basic CHEM 101 with Sihle. My name is Sihle. Thank you very much for watching. I'll see you on the next video. As for now, I'm gone.